What might the future hold in space? There are great opportunities and great challenges before us. I believe fundamentally that humanity will become, in the truest sense of the term, a spacefaring people, and I see four major challenges for the 21st century. The first is activities in low Earth orbit. The International Space Station, currently in orbit, is a foothold in space. It is our base camp in the exploration of the unknown realm beyond. Secondly, our robotic explorers have moved on to all of the planets of the solar system as we endeavor to become, down the road, a multiplanetary species. The use of space for resources, especially power, is an enormously interesting and exciting prospect. Can we build solar power satellites that might be able to beam energy to this planet to overcome all of the needs that we will have in the 21st century? All of those are great opportunities. But more than that is the fourth, and that is becoming a multiplanetary species. Is there an opportunity to inhabit the moon, to inhabit Mars, to create colonies there in which they might engage in resource production, families might live, and we might have an expansive future in space? Will humanity step up and become a bold, multiplanetary species? Will it remain forever here on Earth? Those are the questions to be pondered as we move into space for the 21st century.
Let's take a visual grand tour of some highlights from the combined fields of aerial flight and space flight. This will allow us to use what we've learned and see how it's possible to understand current developments, as well as those yet to come. Let's start with space and work our way back to Earth. One of the key challenges of getting to space, of course, is the cost. Space is expensive because rockets are expensive. The cost for access to Earth orbit is as high as $10,000 per pound of payload. This is largely driven by really high fuel requirements, plus the high costs of building a robust system to survive the harsh environment of space. Also, the lack of reusable components in spaceflight means that the high cost of a single mission cannot be spread across multiple missions, further multiplying the costs. So there are many conceivable business opportunities in space that simply aren't yet viable economically. One idea for reducing the cost of access to space is to combine aircraft and spacecraft together in order to get a combined system advantage that would be low cost. Let's look at the White Knight aircraft and the Spaceship One capsule, developed by Scaled Composites in a push to be the first privately funded spacecraft. So what's the main idea at work here? If a large enough aircraft can be built, a monstrous-sized airplane could lift a rocket assembly to a high altitude for the launch to start there. On June 21, 2004, the White Knight carrier aircraft lifted Mike Melville in Spaceship One up to an altitude of 47,000 feet before the spacecraft separated from the mothership. Now, interestingly, the rocket on Spaceship One used a hybrid rocket for propulsion. This was a combination of solid rocket fuel with liquid oxidizer. The mixing of the phases allows the rocket to retain the low weight and low volatility advantages of solid propulsion and the advantage of a liquid rocket propulsion system that can be throttled, while avoiding many of the disadvantages of each. Spaceship One's rocket could generate about 20,000 pounds of force for a period of about 90 seconds. So after separation from White Knight, Melville fired his hybrid rocket, which accelerated the spacecraft on a suborbital parabolic trajectory. The apex of this trajectory took him to an altitude of 100.124 kilometers, just 124 meters above the Kármán line, the common international definition of the edge of space. So by a relative hair's breadth, Mike Melvill became the very first private astronaut. Following the apex of the trajectory, Melvill deployed the tail fins on his spacecraft in a shuttlecock mode, which oriented the belly towards the direction of flight. This increased the aerodynamic drag and helped the spacecraft decelerate, reaching up to 5 Gs of deceleration. When it reached an altitude of 57,000 feet on the descent, the wing retracted back to its original configuration, and Melvill glided into the Mojave Spaceport for a successful landing. In the process, his team paved the way towards a pair of space flights later in 2004, which won them the $10 million Ansari X Prize for the first non-government entity to build and launch a spacecraft that would go into space twice within the period of 2 weeks. The challenge was a huge hurdle to not only get to space, but to get the spacecraft ready for a second flight in a rapid fashion. This is why Scaled Composites' use of a carrier aircraft was such a great idea. Everything was reusable. Now we can extend this innovative launch idea to larger aircraft that can lift larger rockets, perhaps even ones that could reach Earth orbit and beyond. The main advantage of an air launch is that the total rocket fuel required for Earth orbit goes down, and the one-time use hardware is reduced in size and weight. This is still a huge technical challenge, though, since the payload requirement of the larger carrier aircraft would be massive, making it the biggest airplane ever built. But since that large aircraft would be reusable, the overall system cost would be much lower. Now, the distance to space doesn't really seem to be that far, if we were to take that vertical distance and lay it out horizontally. For example, the 100-kilometer distance to the Kármán line would take a car only about 1 hour to traverse at highway speeds. Or the tallest buildings in the world approach 1,000 meters high, which is 1% of the distance to space. This sense of scale leads us to consider, would it be possible to construct a building that would reach to space? It would have to be only 100 times higher than the current tallest building in the world. Maybe that's plausible. Well, probably not, due to the immense compressive load that the building's foundation would have to support. There's not any material in existence that could sustain that level of loading, so a building that tall would collapse under its own weight. But in a related concept, some have suggested that it would be possible to build an elevator to space without the building. Wow, what a fantastic idea! Just imagine if you could step into a capsule, press a button, and be lifted gradually up into space. How exciting that would be to get to the weightless condition of space after a short elevator ride. The idea for this has been proposed by various scientists over the past 100 years, but it wasn't until Sir Arthur C. Clarke picked up on the idea and published his novel, The Fountains of Paradise, in 1979, that the broader community caught on. Now you may be wondering, without a building, what could we hang the elevator cable from? And that is a challenge. We can actually rely on the concept of conservation of momentum to put an anchor out in space. Let's take a look at a proposed design for a space elevator and consider some of the technical challenges that must be overcome. First, the cable, or tether, that the elevator climbs would have to be counterweighted by a mass that was at least as high up as 35,786 kilometers, the altitude for geostationary orbit. This is necessary to keep the tether under tension. Gravity will be pulling down on the cable, but if the center of mass of the cable is at least as high as a geostationary orbit, then the counterweight will provide the necessary centrifugal force to keep the tether taut. Now, should the tether have a constant thickness or be thinner in some places and thicker in others? The ideal tether would be tapered, with the thickest portion of the tether being at the geostationary orbit level, and tapering to the smallest thickness at Earth and the smallest again at the space anchor end. This approach would maintain constant stress throughout the tether, compared to a uniformly thick tether, which would be too thick at the ends and add unnecessary weight to the tether system. The primary challenge for this tether is the necessary strength-to-weight ratio of the tether material. This is because the tether would have to support its own weight, as well as that of the elevator car and its payload. The strength-to-weight ratio can be expressed as tensile strength divided by linear density. For a successful space elevator to be built, this would require a ratio of 100,000 kilonewtons per kilogram per meter. Metals such as titanium or aluminum don't even come close. Their strength-to-weight ratio is less than 1% of what is needed. Fiber materials such as Kevlar or carbon graphite fiber come closer with only about 10% of the necessary strength-to-weight ratio. The only material that comes close are carbon nanotubes. However, there's currently no way to fabricate these with sufficient length. The longest nanotubes that have been made are only on the order of a meter long. Now, even if a space elevator is built, there's a significant risk posed to the long-term survivability of the tether. Space junk. Yes, this is a real problem. A piece of debris in space could easily collide with the tether and potentially sever it. There is a pileup of debris in orbit from various launches over the decades, and sometimes a decommissioned satellite with leftover fuel can malfunction or explode, further adding to the debris field. Also, there have been tests of anti-satellite missiles by the US in 1985 and China in 2007, which resulted in hundreds or even thousands of pieces of trackable space debris of golf ball size or larger. Eventually, over a period of decades, much of this debris will deorbit and burn up in the atmosphere. But in the meantime, it poses a huge safety hazard.
Now, here's your Pentagon Channel report.
Two large satellites collided in space Wednesday for the first time ever, according to the U.S. Strategic Command. NASA says each satellite was traveling about 17,000 miles per hour when they crashed 485 miles over Siberia. Stratcom tracks all large space debris and is plotting the coordinates for all the large pieces from this collision. Stratcom estimates there are over 18,000 large objects in orbit. NASA says most large orbital debris is upper stage rocket boosters. And a NASA spokesman says they knew a collision of this size was going to happen eventually. Here it is, the big one. Reporting from the Pentagon, I'm Air Force Master Sergeant George Malley.
It's easy to see how orbital debris can lead to further orbital debris through these collisions, in a cascade known as the Kessler syndrome. Destructive collisions can proliferate at a rate faster than the debris falls back to Earth, creating belts of debris where satellites can no longer safely orbit. A variety of spacecraft designs have been proposed, basically to push or pull debris into the atmosphere to burn it up. But all of these are costly due to the high cost of access to space. But as launch costs are reduced, it will become cheaper to protect satellites and clear the way for possible space elevators. Now let's consider yet another reason for high-altitude flight. What if we could fly an aircraft within the atmosphere of a different planet? Is extraterrestrial atmospheric flight possible on Mars? How similar would it be to flight here on Earth? What would be different? This idea is actually not so far-fetched. Researchers at both NASA and the Japan Aerospace Exploration Agency have studied the idea of building an aircraft to fly in the Martian atmosphere. When exploring Mars, these aircraft would offer the tremendous advantage of covering much more ground in a given amount of time. So while NASA's Opportunity rover has traveled well over 40 kilometers on Mars, a Martian aircraft could be designed to cover much greater distances. Now, there are a number of unique technical challenges for Martian aviation compared to flight on Earth. First, and most significantly, the Martian atmosphere is much less dense, roughly 1 or 2% of the air density at the same altitude on Earth. This means that an aircraft attempting to fly on Mars would produce only about 1% of the lift that could be achieved here on Earth. But on the bright side, the gravity on Mars is only 38% of what it is on Earth, so a given mass will weigh 62% less on Mars when compared to Earth. When we combine the lower density with lower weight, then a wing would have to be 23 times larger in order to fly at the same flight speed on Mars. Or for the same size wing, the aircraft would have to fly 5 times as fast in order to stay aloft. So a Martian aircraft requires a much bigger wing, faster speed, or some combination of the two. Now we're beginning to see the challenges of making flight work on Mars. Increasing the wing area is constrained by the fact that the entire aircraft has to fit within a larger spacecraft for transport to Mars. One idea to work around this limitation is to use inflatable wings, which are rolled up for storage on the long interplanetary flight. The inflatable wings can be made out of a fiberglass composite material impregnated with a resin that is ingeniously designed to cure under UV radiation. A pressurized gas canister can be valved to rapidly inflate the wings while the aircraft is descending through the Martian atmosphere via parachute. At an altitude of about 5,000 meters, the aircraft can then be released for either a glider mission or a powered flight of greater length. If instead of a large wing, the aircraft flies at high speed, then there is another conundrum that arises. High-speed flight will increase the Mach number, and compressibility effects, such as shock waves, will become dominant. Also, not only does the higher flight speed increase the Mach number, but the daytime speed of sound on Mars is roughly 25% lower than on Earth, mainly because the air temperature on Mars is lower. To highlight these dramatic challenges, consider an airplane flying at a reasonable flight speed of 75 meters per second on Earth, which is about 146 knots. If that aircraft is at an altitude of 5,000 meters on a standard day, the flight Mach number is 0.23, clearly a low enough Mach number where compressibility effects are not a concern. But that same aircraft, at an altitude of 5,000 meters on Mars, would have to fly 5 times as fast in order to produce enough lift for flight, giving a speed of 375 meters per second. And since the speed of sound at an altitude of 5,000 meters is only 235 meters per second on Mars, compared to 320 meters per second on Earth, this gives a supersonic Mach number of 1.6. Another aerodynamic consequence of the lower density air is a stronger propensity for stall, as revealed by a reduced Reynolds number. With an ambient density that is 1.6% of that on Earth, and a viscosity that is slightly lower than on Earth, the Reynolds number is about 2% of that for the same flight speed and length scale on Earth. This indicates that viscous effects are much more significant on a Martian aircraft, where the thick boundary layer from viscosity will lead to much earlier separation of the flow from the wing's curvature. This combination of high Mach number and low Reynolds number can be horrible for a Martian aircraft trying to pull up out of a dive. The same Mach tuck problem encountered in the 1940s with high-speed aircraft would be much more severe in the Martian atmosphere. On Earth, a somewhat different high-speed challenge comes from the hypersonic plane, one that exceeds Mach 5. Starting with the German V-2 rockets of World War II and moving forward with other hypersonic vehicles, we learned that a flight object can increase the lift-to-drag ratio by riding on its own shock waves. And since the efficiency of flight depends on L/D, a hypersonic vehicle that rides on shock waves can travel faster or farther. In one idea for making use of hypersonic flight, Boeing has proposed a 3-stage launch into low Earth orbit that would start with a reusable supersonic carrier aircraft, then a reusable second-stage hypersonic wave rider, followed by a third-stage rocket. Another idea is Hypersoar, which is a hypersonic concept that calls for an environmentally friendly hydrogen propulsion system, flying at Mach 10 or more, above the atmosphere to avoid overheating, where it would skip in and out of the atmosphere repeatedly until time to descend to the destination. And speaking of environmentally friendly, let's look at a concept for an all-electric aircraft. For example, NASA's Greased Lightning. Here the idea is to reconfigure the propulsion system to drive off electric motors and battery packs instead of burning fossil fuels in the engine. A major advantage is that emissions and exhaust fumes are removed from the aircraft's operating environment. For the airport locale, this improves local air quality and reduces the risk of lead poisoning. Yes, in the US, piston engine aircraft still burn leaded gasoline, known as avgas, as no unleaded alternative has been developed to meet the higher performance needs of aircraft. The use of electric motors can decentralize the production of thrust on an aircraft. This allows a larger number of smaller engines to be used, instead of the few large engines that are used today. Both internal combustion engines and jet engines are difficult to scale down in an efficient manner, so large power plants have traditionally been preferred. In fact, the trend in jet engine design is toward ever larger, more fuel-efficient designs with bypass ratios approaching 10, with 10 times the mass flow going through only the fan section compared to the core of the engine. But electric motors can be scaled across a wide range without significant changes in efficiency, allowing for a higher number of smaller engines to be distributed across the airplane. This offers distinct advantages in reliability, Aircraft designers no longer have to worry about designing for the strong asymmetric thrust case to keep the aircraft under control in the event of a single engine failure. Use of a large number of small engines also minimizes the loss of thrust if a single engine were to go out. Other advantages include the distribution of weight across the span of the wing. This weight distribution can offset the lift produced by the wing, which reduces the bending moment at the wing root. With the altered loading, the structural weight of the aircraft can be reduced, which results in fuel savings over the long haul. And finally, the use of distributed electric propulsion can also have positive aerodynamic effects. The wake from each distributed propeller can be blown over the wing, which provides a bit extra lift at low speeds, allowing the size of the wing to be reduced, and a smaller wing will give higher wing loading, which enables the aircraft to fly faster and more efficiently in cruise. These electric aircraft concepts have led to a push towards solar-powered flight, like on the Solar Impulse 2. The idea is a compelling one. If the efficiency of solar cells is great enough, and battery storage capacity and reliability are good enough, we can put up an aircraft indefinitely. Aircraft flying at very high altitudes will be above the weather and the clouds, making persistent daytime solar energy collection a straightforward matter. If the battery capacity is high enough to keep the aircraft aloft throughout the night, then the aircraft could stay aloft indefinitely. These capabilities allow persistent aircraft to take on at least some of the roles of orbiting satellites, but at a much lower cost. This is critical for persistent internet in remote corners of the globe, for example, a technology driver that motivates the leading Silicon Valley corporations. It's this technology push that has led the biggest Silicon Valley tech companies to start their own aircraft projects, which is changing the landscape of the aerospace industry. Long-endurance solar-powered technologies were demonstrated on a round-the-world flight of Solar Impulse 2, piloted by Bertrand Piccard and André Borschberg, in a tag-team fashion, alternating each flight with only one pilot on board at a time. This aircraft, with 4 electric motors and an array of wing-mounted solar cells, became the first solar plane to complete a non-continuous circumnavigation of the globe in July 2016. Since the aircraft weighed in at only 5,100 pounds, but had a wing area of about 2,900 square feet, the wing loading came in at less than 2 pounds per square foot. This drove the Solar Impulse to a very low cruise speed of 56 miles per hour during the day and 37 miles per hour at night. Can you imagine the personal endurance required to fly around the world at that low speed? Some of the individual legs of the flight were amazingly long. For example, since there are very few suitable landing sites during a crossing of the Pacific, the longest leg was an incredible 4,800 nautical miles. It took almost 118 hours, nearly 5 days, for that leg alone. That's pretty amazing when you consider that there was only one pilot on board to pilot the aircraft nonstop. With all of these pieces in place, the next challenge becomes persistent flight of an aircraft at high altitude by an unmanned system. Currently, there are autopilot systems on piloted aircraft where it's routine for the autopilot to complete the entire trip under automatic control, but under the pilot's supervision. There are also drones that are remotely piloted by teams on the ground. So if an aircraft can fly itself and can fly without a pilot on board at all, why not go to higher levels of autonomy and have the aircraft fly itself without a pilot on board? This is a wonderful vision, but also an incredibly tough challenge. The operating environment is highly complex, requiring nuanced judgment on the part of a pilot to maintain safety of flight. For example, only an experienced pilot looking out the window can infer the danger developing with a large cumulonimbus cloud forming in a spot that was not predicted by the weather forecast and isn't yet showing up on radar. The safe response is to give the developing thunderstorm a wide berth, flying away around the cell so the plane can avoid the strong updrafts or downdrafts that could lead to serious problems. This very common scenario in aviation poses a tough challenge to a fully autonomous system due to limitations in perception and cognition of the autonomy. It's an active field of work, so we may one day see fully autonomous aviation systems. In the near future, I think we'll likely see personal air vehicles, where many of the vehicle's functions are automated, but not fully. A pilot of such a vehicle would not necessarily have to be trained in the traditional stick and rudder skills that today's pilots need for safe control of the aircraft. Instead, pilots of these aircraft with enhanced autonomy would only have to provide high-level decision-making to reroute the aircraft around dangerous spots, for example, to circumnavigate a developing thunderstorm. And for safe operation of personal air vehicles, flying without highly trained pilots, it's important to have some kind of safety net or backup system in case things go horribly wrong. If the engine fails on the personal air vehicle, an untrained pilot would not know how to guide the vehicle in for a safe landing. So what could be done? What about a parachute? Not just for the person, but for the entire flight vehicle. That way, both the person and the vehicle could be saved in the event of a failure. Well, this idea is actually already out there on some aircraft today. Aircraft made by Cirrus have a built-in parachute for the entire aircraft. Even their jet has a parachute. Now let's see if we can estimate how big that parachute needs to be. If the aircraft is in a steady descent under the parachute canopy, meaning it has already reached terminal velocity, then we can say that all of the forces are in equilibrium. So the drag must equal the weight. To come up with the drag acting on the parachute, we can use the drag equation that we saw in the first lecture. Drag is equal to the product of 1/2 times density times the square velocity times the parachute canopy area times a drag coefficient. Let's take the weight of the aircraft as 3,000 pounds and assume standard sea level density. Also, a typical drag coefficient for a parachute might be 1.75. And let's limit ourselves to a descent rate of 1,500 feet per minute, or 17 miles per hour. Solving the drag equation for area gives a required parachute diameter of 54 feet. That's a pretty reasonable size to pack into the top of the fuselage, measuring about 5 feet wide. So in the event of an engine failure, all the pilot has to do is pull the ripcord and sit tight until the entire aircraft comes in for a landing, and hopefully in a place that's not too inconvenient. Another efficiency-enhancing effort in aviation is the continual push for reduced drag. We've discussed some ideas like laminar flow control, but there's another intriguing opportunity for drag reduction if we're willing to sacrifice some operational flexibility of an aircraft and stay near the ground. From the earliest days of aviation, pilots have noticed that the aircraft would tend to float on landing when it was within about one wingspan's length from the ground. In this near-ground region, the aircraft experiences increased lift and a reduction of induced drag, known as ground effect. Ask your friends to guess why, and you may get a lot of different answers. But the actual reason for increased lift so close to the ground is that the presence of the ground alters the flow around the wing, providing an obstruction to the downward directed flow behind the wing. Looking at the flow over a wing in ground effect, we can trace the stagnation streamline from far upstream, where it will be very close to the ground. As we move along the streamline closer to the wing, it rises up to reach the stagnation point on the leading edge of the wing. So the area between the stagnation streamline and the ground will dramatically increase as it reaches the wing, causing the velocity to go down and the pressure to go up. With the presence of the ground, this effect is more pronounced, so there is greater pressure on the bottom of the wing than would be encountered in free flight out of ground effect. So we can think of the wing as riding on a cushion of air underneath it. Other phenomena resulting from a wing in ground effect are inhibited downwash and reduction in the strength of the tip vortices. This is why the induced drag goes down while the lift goes up at the same time. These two trends dramatically improve the efficiency of a wing in ground effect. There have been a few aircraft built and flown that rely on ground effect for efficient flight. Russian designer Rostislav Alexeyev was behind the development of several massive Ekranoplan aircraft, measuring hundreds of feet long and weighing over 500 tons, that flew over 300 miles per hour just a few feet above the water. These vehicles actually depended upon ground effect. Otherwise, they couldn't generate enough lift to fly. But with that efficiency gain, Alexeyev was able to build huge vehicles that would skim a few feet over the top of the Caspian Sea. In fact, when the CIA caught sight of the testing of this new aircraft, they were deeply unsettled by its capabilities and dubbed it the Caspian Sea Monster. The downside of these amazing wing and ground effect vehicles, though, is that they must be operated over water in order to avoid ground obstructions. and a pilot can't bank the aircraft very much without dipping a wing into the water, which would cause it to crash. We can also look to nature to see birds who rely on the ground effect. Consider the pelican, for example, which often skims just above the surface for long-distance flight. The pelican can save energy and minimize flapping its wings by flying in the ground effect. Now that brings us to our concluding thought for this course. Let's return again to the question, why do birds flap their wings, but aircraft do not? Most birds regularly flap their wings in order to stay aloft, but nearly every man-made aircraft ever built does not have flapping wings. Why is there such a discrepancy? Are there different physics involved for birds and airplanes? Well, the physics are the same no matter what the object is that's flying through the air, as long as we appreciate the full, comprehensive view of the physics involved. Despite the differences between birds and aircraft, the overall guiding principles of flight are the same. The great flight diagram that we saw in the first lecture is a blueprint for scaling, where the wing loading and flight speed of an aircraft follow a general trend of increasing with higher weight. And ultimately, the same physical phenomena of lift, drag, thrust, and weight all come into play to govern the intricacies of flight. Now, I hope that you found this course to be a journey into understanding the science behind the flight of aircraft and spacecraft. Beyond just gazing in wonder at these amazing vehicles, you can now explain to your fellow passengers on an airplane flight what the pilots are doing, why your aircraft is put together the way it is, and much more. And beyond that, I think we can all look forward to those who will build on this scientific understanding and go on to create the next generation of flying vehicles. Until then, blue skies and tailwinds.